So, let us see one more technique of improving the accuracy of this first order derivative. So, this is so let us call it a higher order or higher accuracy method again for first order derivative. So, we will use the Taylor series that we have been using plus a h f prime f x plus a h square by 2 factorial f double prime x, and then what we neglect because of the truncation is h cube. So, just to remind you that we have, of course, we can ignore completely the double derivative and can arrive at a formula for the first derivative or the first order derivative, that is f prime of x. But here, instead of that, what we shall do is we will include the definition of the second order derivative and get an improved estimate or a more accurate estimate of the first order derivative. So, to remind you that the second order derivative is second order derivative necessarily involves 3 points, which could be f x minus x x plus 2 h, f of x plus h and f of x, or it could be f of x plus h, f of x and f of x minus h, it does not matter. So, here we are writing it involving x plus 2 h, the value of the function at x plus 2 h, at x plus h and at f of x, that is at x. So, it is x plus 2 h minus twice of x plus h and a plus f of x, and this is nothing but divided by h square, and we are leaving out terms which are of the order of h. So, we have used, of course, in the previous definition we might have used points such as f of x plus h, x and x minus h. Here we have used 3 different points, that is x plus 2 h and x plus h and x, but as I said that it does not make a difference. So, if you put, call this as 2. So, if you put 2 in 1, that is I am going to put this second derivative into this third term that appears here and then do slight bit of rearranging, then we get as f x plus h minus f of x divided by h, which is our original definition, and then there is a h and f of x plus 2 h minus 2 f of x plus h minus this is plus f of x. So, this is divided by 2 h square, because there is a 2 factorial which is nothing but 2, and then if you realize that what we are leaving out is h square of the order of h square. So, if you rearrange or rather simplify this, this becomes equal to f of x plus 2 h and 4 f x plus h minus 3 f of x divided by 2 h and plus of the order of h square, and this so this is of the order of h square. So, this is the derivative formula for the derivative that you are one can use by explicitly using the definition of the second derivative. So, this is another formula. So, instead of using the forward difference or the backward difference or the the finite difference, rather the using a 3-point formula, we can also use this definition of the second derivative and put it into this equation or into this formula to compute the first derivative. So, let us see that how is it any better than what we know. So, let us take an example. All right. So, this is like f of x equal to minus 0.1 x to the power 4 minus 0.15 x cube minus 0.5 x square minus 0.25 x and a plus 1.2. So, that is the function that is given, and find the first derivative, that is f prime of x at x equal to 0.5 using this method, and this method is called as a finite divided difference method. So, let us just write that. So, this is called as the finite divided difference method. All right. So, using this, using a finite divided difference method, that is the one that we have just learned, which involves computing the or using the second derivative into the formula. So, and it is given that use h equal to 0.25. Okay. So, the solution is as follows. So, you have x minus 2h is equal to 0, because x is equal to 0.5 and 2h is equal to 0.5. So, this is 0. So, f x minus 2h, it is equal to simply 1.2, or I will write it with up to 4 decimal places, because we will use that. This is just an arbitrary decision by us to use it for 4 significant digits. X minus h is equal to 0.25, and f of x minus h is equal to 1.1035. So, if you put 0.25 into this, then we can calculate this and it comes out as 1.1035. X equal to 0.5, f of x is nothing but equal to 0.9250, and x plus h, which is nothing but 0.75. So, f of x plus h is equal to, it is equal to 0.6363, and finally, the x plus 2h, which is equal to 1. So, f of x plus 2h is equal to 0.2000. Okay. So, these are the values that we are going to need, and we can compute this using this method, the method that we have just said, and so on. So, f prime evaluated at 0.05 using that formula, using this finite divided difference formula, this is equal to minus 0.2000 and 4 multiplied by 0.6363 minus 3, 0.9250 and divided by 2h. So, 2 into 0.25. So, if you compute these correctly, then it comes out as 0.8594, and the exact value of this, exact value you can determine by, because it is a 4 into 0.1 x cube and then put x equal to 0.5 and so on, and then do this. So, exact value is equal to 0.9250 0.9125, and so error, if you want to calculate this error, so this is like minus, which I should not forget. So, it is a minus 0.9125 and a minus of minus 0.8594 divided by minus 0.9125, and if you want to convert it into percentage, then it is this. This comes out as 5.82%. So, using this finite divided difference method, one gets an error of nearly 6% of error, and one can actually test that with a lower accuracy method, that is finite difference, forward difference or backward difference, or even the divided difference method, what one gets. So, this is one example that we have. Now, let us learn about another method, yet another method, which is much more accurate, and we will see that using the same example that you have seen here, and that method is called as the Richardson's extrapolation. Okay. So, what is Richardson's extrapolation? So, just to put things in perspective, so far we have seen two ways to improve the derivative of a function, and one is that of course, decreasing the step size. This was not told explicitly, but you should discover it yourself, that if you have a step size of 0.1, you would get some result, that is we are talking about h, the step size h, and instead if you take a step size of 0.05, then you would get an improved accuracy, because you are taking the values of the function at really neighboring points where you want to calculate the derivative. So, you are closing in the gap between the 2 points where you are computing the value of the function at both these points. However, this also comes with the risk of having, if you have too less of a step size, then the computer actually might get confused that to be 0, and there will be a division by 0, which is certainly not expected. But to a certain extent, like in the last example, we have taken a step size of 0.25, we could have reduced it to 0.1, and we would the 5.82% of that error that we have obtained would certainly go down. Okay. So, this is one way of taking care of the accuracy of the derivative. And the other thing is that which we have mostly used, is that I use a higher order formula. All right. So, if these are the two methods that we have seen so far, what is this Richardson's extrapolation that is going to improve it? And we will see that it actually does a remarkable improvement of computing the first order derivative. So, so this Richardson's extrapolation uses two derivative estimates to compute a third one. So, let us illustrate. As follows. Okay. So, So, the basically the estimate and the error, basically we are talking about the truncation error and the error that are associated with a differential algorithm is d, that is the differential algorithm or the derivative that we are trying to compute. It is d as a function of h, which depends on the choice of h, and hence the truncation error will also depend upon the choice of h, and h, needless to say, is the step size which appears in the denominator of derivative. So, just to make our notations clear, d is the exact value of the derivative, d h is the approximate value derivative with step size h, and E h is basically nothing but the truncation error. Associated with the step size h. So, if that is true, then let us make two estimates using two step sizes. Namely h1 and h2. So, we will make two estimates of the same formula for two different step sizes h1 and h2. In principle, h1 and h2 could be independent, but we will see that we get a particularly simple formula if h1 and h2 have a relationship in between them. So, we will have the dh1 plus eh1, that is the error associated with h1, or rather this is the exact value of the derivative for the choice of h1, is same as dh2 plus eh2. So, we choose the h1 and h2 such that basically the second, so your second derivative, so this can happen if your f double prime x, which is the second derivative, is independent of the step size. Okay, because this double derivative will come into the expression of this Taylor expansion, and if that becomes independent of the step size, then we can write this for two different choices of h1 and h2 to be like this. Assume, or rather it is an assumption, but at the same time this assumption we have seen that this h1 and h2 are related, or they are only the truncation error is occurring only at the square of h1 square and h2 square. Refer to the discussion that we had last time about the truncation error. We are now assuming that it is not of the order of h, rather it is of the order of h square. So, E of h1 is nothing but proportional to h1 square, and E as for h2 is proportional to h2 square, such that we can write down eliminating the constant of proportionality that the two errors are in the ratio h1 square by h2 square, which is nothing but equal to h1 over h2 whole square. This importantly what does is what it does is that it importantly removes the second derivative from the problem. Okay. So, in any case we have to see this how it goes. So, we have a E h1 is nothing but E h2 and h1 by h2 whole square. So, we are going to reduce it to one variable, that is E of h2. So, if we write it in this expression, let us call this as 1 here, we need to distinguish it from the one that we have written earlier. So, we write it in Roman 1 and 2. So, putting this Roman 2 in 1 we have a d which is equal to or rather the dh1 plus dh1 plus, now EH1 I am going to replace it by this expression. So, this is EH2 H1 by H2 whole square. So, I am using two different step sizes, and it is equal to DH2 plus EH2. And if you compute or rather solve for EH2, then it becomes equal to DH1 minus DH2 divided by 1 minus H1 by H2 whole square. Okay. So, that is the formula for E of, or rather that is the error associated with this choice of H2, which is the second choice for this step size. So, what is it good at? So, now we have done the truncation error is estimated in terms of the derivative and the step size. And the step size. Okay. So, so this can be substituted into this last one, let us call this as 3. So, equation 3 can be substituted into the parent formula, so to say, which is D H2 plus E H2. So, this is equal to a D H2 plus a D H1 minus a D H2 1 minus H1 by H2 whole square, or we can simply write it as DH2 plus a DH2. We can change the sign of both the numerator and denominator and can write it like this. Okay. So, this is the error associated with H2, which are computed in terms of the values of the derivative at H1 and H2, where those derivatives can be either used using a forward difference formula or a backward difference formula or a central difference formula, so to say. In particular, if you choose H2 equal to H1 by 2, then one can have a D which is equal to dH2 plus 1 divided by 2 square minus 1 dH2 minus a dH1, because this thing becomes a factor of 2 and so on. So, this if you rearrange things and so on, it comes out as 4/3 d of H2 one choice minus 1/3 d H1 the other choice. So, that is the formula that one can use in this Richardson's extrapolation. So, we will call it as Richardson's extrapolation formula. Okay. All right. So, this is the formula that we use for two different choices of H1 and H2, and then build up a third. Let us see how this is more accurate, or if at all it is. So, I will write down the example, the same example once again. So, we have, just to remind you, so that you do not have to flip the pages or rather rewind the video. So, it is this minus 0.5, I think we made a mistake, it is yeah, that is fine, 0.5 x square minus 0.25 x plus a 1.2. And again calculate the derivative f prime of x at x equal to 0.5, in which case use h1 equal to 0.5, h2 equal to 0.25, because H2 is nothing but H1 by 5. So, this is the thing that is given, and H2 we have automatically taken it to be the half of that H1. So, D at 0.5, 0.5, that is H equal to 0.5 is nothing but 4 by 3 D equal to 0.25 minus 1/3 d 0.5. Okay. So, this is the thing. Now, you have to calculate this d at 0.25, which you can use any of the methods. We have used one particular method, and this is like 4 by 3 into minus 0.9344 minus 1/3 of minus 1, and this is equal to minus 0.9125. So, this is absolutely exact. That of course, has has made us calculate these two derivatives at 0.25 and 0.5 using the best formula. So, we got the exact result using this Richardson's extrapolation. Okay. So, this is yet another improved method of calculating the derivative, and of course, in a particular case it gives you a result which is equal to exact result, which otherwise you would have gotten if you do it analytically. This was just a coincidence that we have calculated this d at 0.25 and d at 0.5 for using formula which finally give you this. Okay. But it certainly is a better estimate of calculating the derivative. Now, let us look at a practical issue of computing a derivative for unequally spaced point. So, sometimes when you are doing an experiment, you may not be able to take data at regular intervals, or even if you do that, there are some regions where the function is having an pathological behavior, that is, the function is, say, blowing up, or the function is having a kink, or it is having a non-monotonic behavior. You need to take much more data points there than at the places where the behavior of the function is smoother. So, in those places where you need a derivative, that is where the density of points are much more than at other places. So, we can have a data set which are unequally spaced, and for this unequally spaced data set, we can use the Lagrange's interpolation polynomial that we have learned earlier and analytically take the derivative. I will simply write down the formula, and you can look at the Lagrange's polynomial, that is interpolation polynomial, and can convince yourself. So, we will use Lagrange's interpolation scheme. And we are particularly taking it for 3 points, using 3 points, and analytically differentiating it for a particular point at, or rather not for, let us call it at a particular point, say x 0. x 0. Okay. So, what I mean to say is that the f prime at x 0, just like in the previous example, the x 0 is nothing but 0.5. So, we will use this x minus h, and then this is that what we called as Li. It is 2 x 0 minus x plus h, and this is x minus h minus x. These are the data points. So, these are like xi's, and these are xi minus h. So, do not cancel x from here. So, this is the data point which is on the left of x, differing by an amount h with a step size h, and this is this the data point at x, and so this is like x minus h and a minus of x plus h. Okay. These are the two data points, and there is a value of the function at these left point, and plus f of x and 2 x 0 minus x minus h minus x plus h, and then there is x minus x minus h and x minus x plus h. These are analytically done from the Lagrange's interpolation polynomial. You need to go back and check with the formula that we have written down there, and similarly x plus h is nothing but a 2 x naught minus a x minus h minus a x n divided by x plus h minus x minus h and x plus h minus x. Okay. This is the and there is a formula for using by using the Lagrange's Lagrange's interpolation scheme, it of course does not require you to have equally spaced data points. You can have any 3 points. Of course, here we have shown the 3 points as x minus h and x plus h and x, but in principle this works for any. So, we can have a x minus h 1 and x plus h 2 and things like that, and we can build the same formula for the derivative. So, this is for the used for the unequally spaced data points. As I said, this is particularly relevant when you have an inflection or if you have an upturn of a certain function, non-monotonic behavior of certain function, and that requires you to take much more data points in the vicinity of that inflection point or that upturn. In which case, if you need to find out a derivative there, you need to use this is only used 3 points, but you can use more points, particularly in the context of an upturn or a non-monotonic behavior such as this. And so, you may have a density of data points to be very, very large here, whereas not so many data points once when the function becomes smooth, like here you may not have those many data points and so on. So, this is the main idea behind that. So, this is analytically obtained and then you put it back into this into the computer to compute the value of the function, say at a given point, let us call it as x 0. I mean, we are simply saying, so this is your x and so on, and this is your f of x. I am just giving you a crude example of this. So, this is by and large about derivative. Once again, I reiterate that derivatives can become a risky operation in a computer because of these smallness of the denominator, and sometimes the difference between quantities in the numerator can also be small. So, these smallnesses are not really a good thing for a computer to compute. So, sometimes some derivatives are actually replaced, or rather differential equations are replaced by integral equations, whereas integration is a much easier thing and a much more accurate thing to perform using a computer. However, nevertheless, you still need to learn how derivatives are computed, because if you need to have a very direct answer to a question that where in the parameter space the function has a minimum or the function has a maximum, one needs to calculate the derivative at all points in the vicinity of certain points which are hunched to have or which are suspected to have the housing the the minima or the maxima.